name is Brittany Wenger. I'm a student at Duke University, and I'm a senior majoring in biology. I'm also the creator of Cloud for Cancer, a breast cancer detection app. The way Cloud for Cancer works, just as a brief overview, is it takes information from fine needle aspirates. FNAs are the quickest, cheapest, and least invasive form of biopsy a woman can have. However, they're also wildly inconclusive because there are very subtle patterns. I wanted to improve breast cancer diagnostics by creating a computer program that could help doctors in recognizing these patterns. I did that by creating an artificial neural network, because neural networks are these incredible programs that can literally transcend human knowledge. They model the way the brain's neurons and their interconnections work so that they actually learn how to detect really complicated patterns. Once I created an artificial neural network that was detecting breast cancer from fine needle aspirates, I wanted to deploy it to the cloud, because the cloud is just this incredible elastic entity that can scale to support usage by every hospital in the world. So I want to take a few steps back, because people often ask me how I got interested in science. I don't fit the stereotypes of what they think a scientist should look like. I like to hang out with friends, I put my family above all else, and I was a very competitive soccer or football player back in the day. My best answer is I'm inspired by science. I was that kid who never outgrew the why phase, but it wasn't until I found science that I found my answers and more questions. With science, the more you know, the more you wonder. It's an infinite process, and that's why I love it so much. I first got interested in computation specifically when I was 11 years old. I was taking this elective course on futuristic thinking, and I came across the concept of artificial intelligence. I was enthralled by the fact that the computer could learn how to learn. I went home, I bought a textbook to teach myself how to code, and I started coding. My first big project, because I do love soccer, was actually a program that learned how to play soccer. I had these X's and O's running around the computer, and as the X's learned when to pass versus when to dribble versus when to shoot, they would start to win more and more games against control groups which weren't learning. At one point, it was about 95% of the time the neural network would win. However, when I was 15, I found yet another source of inspiration. I really wanted to combine my dual passions for computer science with this newfound interest in breast cancer to improve the diagnostic process. My cousin was diagnosed with breast cancer, and I saw firsthand the impact has on a woman, and this disease has on a woman and her family. What's startling is that in the United States, 1 in 8 women will be diagnosed with breast cancer in her lifetime. And unfortunately, these statistics are rising. Here in Chile, for every 100,000 women, 40 are currently undergoing some sort of battle with breast cancer. For these women to survive and to have the least negative outcomes, it's really important for early detection to be available. That's again why I was so interested in using fine needle aspirates to create a tool for doctors. Fine needle aspirates work by a doctor sticking a fine needle into a palpable breast mass. The process causes the patient about the level of discomfort of a blood test. A few cells are extracted, stained, and then analyzed under a microscope. And doctors from that will try to determine whether the mass is malignant or benign. The reason why fine needle aspirates are so difficult to diagnose is the same mass can show attributes of a non-cancerous mass and a cancerous mass. Even though clearly the answer is binary, you can only have either cancer or not have cancer. To illustrate this point, I want to show you a couple fine needle aspirates. I'll start with a disclaimer. These are not masses that are considered difficult to diagnose. These are easy masses, so you can only imagine what a dubious mass does look like. So the first mass is benign. And some of the reasons a doctor may have realized that is that the cells are about the same size and about the same shape. But if you look at the really dark parts of the mass, those are the nucleoli. They are very prominent, and there are multiple per cell. That's not normal, and that's an indicator that this mass may be cancer, even though it is in fact non-cancerous. The second mass, the one on the bottom of the slide, is also a benign mass. For this mass, you can really tell because the cells are so close together. The marginal adhesion is great. However, there are portions of the mass that are multi-layered, and usually you would only see that in a cancerous mass. The final mass on the far side of the slide, the tallest one, is actually cancer. And the telltale sign that it's cancer is that the reproduction activity is completely irregular. You see cells dividing at the wrong stages, cells dividing all over the place. However, there are some very pale cells in that picture. Those cells are devoid of their cytoplasm, and that's not something you usually see in a cancerous mass. You would usually see that in a benign mass. I show you this to illustrate why a computer program has so much potential when it can recognize these patterns and these sort of algorithms that are far too complex for a human just to look with their naked eye and realize. Creating an artificial neural network is not an easy task, especially when you're working on your bedroom floor. I was 15 when I started this, and it's something that was really an iterative process for me. In science, you learn just as much from your failed experiments as you do from your successful ones. So I actually spent a year and a half of coding this program. The first iterations had more errors than code, and I never got them to compile. And the second full iteration that I spent about 4 months working on, it finally compiled, and I was so excited, but it was solidly worse than flipping a coin at diagnosing breast cancer. What I did is I went back and said, OK, why is this second implementation failing? And I was really able to come up with some novel algorithm components that help my model that is having success now. So the way the current Cloud for Cancer program works is it feeds in these 9 different attributes which are based on cell morphology, how the cells look. Things like clump thickness, are the cells mono or multi-layered, or marginal adhesion, how much are they sticking together? Doctors rate these attributes on a scale of 1 to 10. 1 being this particular attribute looks very characteristic of a benign mass, 10 being this particular attribute looks very characteristic of cancerous. Of course, nothing's ever that cut and dry because these aren't really easy diagnostics, so usually you have things somewhere in the middle of that scale. These logical inputs are then converted into their binary representation, so a series of 1s and 0s. If you think about our biological neurons in the brain, they're either firing or not. So converting the values into binary makes the program all the more brain-like. The artificial input layer then makes 216 connections with the hidden layer. And all these connections are actually math, so they represent the synapses in the brain. So in between the artificial input layer and the hidden layer, there's a corresponding weight matrix. And at first, the values in this weight matrix are random. The weighted values are then summed up and sent to a sigmoid activation function, which is like an S-shaped curve, that again converts the value on a scale of 0 to 1. Because if it's 1, we know that this connection is really helpful for the network. We really want to consider it highly. And if it's 0, we're saying, go away, you don't matter, please leave our model. A similar process then occurs between the hidden layer and the output layer until the program reaches a response. Now, this is a neural network, meaning it's learning based on its experiences and mistakes. So in training mode, it knows whether a particular mass did end up being cancer or not cancer. So it'll say, if I diagnose this mass correctly, I can leave my algorithm as is. But if I didn't, I need to go back through and update my weight matrices so that I can diagnose the next mass correctly. The reason I'm really passionate about using neural networks for cancer detection is that cancer cells are constantly mutating and changing, and there are a lot of different types of breast cancer. And my model can also adapt to these changes in cancer or changes in frequency of different types of cell morphology. So far, I've run a series of 7.6 million trials. For one period, I was setting my alarm every 4 hours, day in and day out, to check the accuracy of my program. And I'm really excited to say that it's over 99% successful at diagnosing cancer patients correctly. However, this is science, so one question leads to another question. And through these 7.6 million trials, I saw that my network would get even better as I got more data. That's why I decided to deploy the network to the cloud, because the cloud is just this incredible entity that allows for me to have infinite server space, so that if every hospital in the United States and in Chile decided to use my program tomorrow, I would have the capacity to handle that. It also facilitates the acquisition of future data samples so that my network can continue to get smarter. If you think about physicians, they're really busy, so it's really important that a tool is easy to use. Using the cloud, it's working as an online app. You can check it out at cloudforcancer.appspot.com, and it's doing great. But if some doctors maybe are using iPads in practice, then I can code a really quick client and put it into my program and call my program from the cloud so that doctors can use it on their iPad. Other hospitals still may be using old PC systems, so I can easily create a platform for that. There's a lot of malleability when you use something like the cloud. I think the most important thing I've learned throughout this whole process is that persistence pays off. There were a lot of times that my program was failing, but for me, I just really loved the puzzle, and I loved asking these questions. And if there are any young scientists in the audience, I hope that you also love kind of the thrill of not knowing what's going on and the eventual finding out of both what's going on and how much you don't know. And this might sound like the end of my talk, but it's not, because in science, it's such an iterative process. So after the program was diagnosing breast cancer, I was really curious as to whether it could be extended to diagnose many, if not all types of cancer. I decided to focus first on leukemia because for a number of reasons. One, I'm an aspiring pediatric oncologist. I'm 22 years old, about to graduate with a biology degree. But in the United States, after undergraduate, you go to 4 years of medical school. So I'm headed off to medical school soon and want to work with a pediatric population. Leukemia is one of the biggest diagnosed cancers in pediatric patients. Another reason I was really interested in mixed lineage leukemia in particular is that it's a very aggressive form of cancer that's caused by part of one chromosome translocating onto another chromosome. This creates a slew of fusion proteins that drives a really difficult behavior. Only about 40% of patients who have this subtype of leukemia survive, and that's really sad when you consider the fact that infants and people who have secondary cancers are most likely to be diagnosed with MLL. Also, leukemia is really different from breast cancer. So if you think about it, leukemia is a cancer of the blood, whereas breast cancer deals with solid masses. So I figured if my program could work with leukemia and breast cancer, that was a good indicator that it may be extended to multiple types of cancer. The leukemia information I found is actually microarray data, so there are over 40,000 inputs per person. The numbers are on a scale of negative 20,000 to 20,000, so it was very different from the original breast cancer data. What I found was that with a slight change in the statistical preprocessing and with some customizations, it had a lot of success in diagnosing leukemia. Now, mind you, the sample size is small, but it's diagnosed 100% of MLL patients correctly. Additionally, it identified 4 proteins that were particularly influential in the network's decision. So I think this may be an indicator that these proteins are candidates for drug targeting in the future, and they may be these fusion proteins we talk about that drive the aggressive behavior. I'm a student at Duke University, and I've been really lucky to find 2 incredible mentors, Dr. Jeff Ginsburg and Dr. Ashley Valente, who have continued to help me expand my work in using artificial intelligence for biomarker and biological discovery. Lately, I've been doing a lot of work with influenza because influenza is a disease that impacts a lot of people, and it would be really useful to know whether somebody was going to get the flu after they're exposed before they hit peak symptoms. The influenza data I'm working with is huge data. It's this classic big data we talk about. There are over 50 million sequence reads per patient per time point. But using my program, I've been able to identify whether people will get the flu or not after they're exposed earlier than peak symptoms with 93.5% accuracy. I've also tried some other artificial intelligence algorithms that have actually had more success. You see the highest one was actually 98% because they're more known for working with big data. And as we get more subjects, it'll be interesting to see how these sort of artificial intelligence programs continue to learn and which one is ultimately the best. The other thing that's really exciting about the influenza program is it's able to identify particular proteins that may be involved in host response to infectious disease. So we're getting an inside look and a novel look at that into what might be driving response and host immune system. I want to be clear, I wasn't some kid who was born with a beaker in my hand. I'm not a genius, and you don't have to be a genius to do science. Outside of the lab, I find that keeping a balanced life really does help me come up with these cool ideas. So whether that be through playing Quidditch, which is based off of Harry Potter, and yes, we do run with brooms, or continuing to play soccer at the recreational level, or volunteering at the Duke Children's Hospital, or through Google's Made with Code program, which is a program that inspires other girls to get interested in coding. One of my favorite opportunities we had was to mentor the girls to light the national Christmas tree lighting in the United States, so they actually got to do the patterns of the Christmas tree and see their kind of solution come to life in front of Tom Hanks and President Obama. This is the Congreso Futuro, so I don't feel like this would be a complete talk unless I address the future. So for me, my future involves going to medical school. I'm about to graduate in May from undergraduate with a degree in biology. I'm headed to New York City to study medicine at the Mount Sinai School of Medicine. I'm really interested in precision medicine, and I think this is a really exciting direction that medicine is going, which kind of deals with subcategorizing individuals and subcategorizing disease risks based on genetics, environmental factors, personality, etc., so that we can really personalize both treatments and intervention strategies to what will help each individual the most. I'm really excited to be presenting in this particular panel because you're about to hear from your young Explora scientists. They're amazing, and I think that young people in science really are the future. We're facing a lot of challenges, many of which have been addressed on this stage, from global warming to finding the cures for cancer, to finding new ways for space travel. There are so many things that our generation and the current scientists, so many questions to solve. And I know that as we get more young people interested in science, we're going to find even more excited solutions and even more exciting answers. You don't have to be a genius to get involved in science. You just have to have a question. Thank you so much.